Okay, this is Dr. Matthew J. Traum. The purpose of this video is to share with you the vector math underpinning tolerance loops. This is a follow-on to the lecture that I gave in class today. I didn't get to this part for most classes, so it's just meant to get you up to speed on the math underpinning this technique that we're going to use in class. So we're going to find what's called a series of closure equations. Closure equations. And these equations, this is really kind of a UF term. UF terminology. I have not heard this technique referred to as closure equations anywhere else but here. So this might be unique to our university. But essentially, all we do is just recall how vectors work. So recall how vectors sum together. And to jog your memory, I'm going to just have some surface, and I'm going to put my coordinate system down on the surface. We're going to call this the x hat direction. This is the y hat direction. And maybe right there is the origin. All right. And I'm going to now just have a couple of vectors coming off of this surface. So I'm going to use a couple of different colors. Hopefully the blue shows up slightly different than the black. So there's one vector. We'll call that R1. Have a second vector that starts from where R1 finishes. We'll call that R2. And then we'll have a third vector. And third vector is going to be slightly different in that it's going to intentionally be set so that it goes all the way back here to the origin. So let's see if we can draw this straight. There we go. Okay. So this third vector goes all the way back to the origin, and we're going to call that guy R3. Okay. Now, I'm going to just remind myself that R3 is called the return vector. It's slightly different than the others in that it goes back to the origin. Okay, so it goes back to the origin and stops there. Okay, so now if I want to sum these guys up, very easy to do. I'm just going to say R1 plus R2 plus R3. And what does that equal? Well, what I'm actually doing by summing these vectors up is I'm walking from the origin up R1 to there, and then I'm walking from R1 to R2 along there, and then I'm walking down along R3 back to the origin. And so all I've done in taking the path of those three vectors summed up is got myself right back to 0. So those guys sum up and give me 0. Now, the other thing that I can do is I can look at what happens in just the x direction and just the y direction. So if I'm interested in the sum of just r hat in the x direction, r in the x direction, and r in the y direction, x hat and y hat directions, really what this looks like is I'm coming along here. We'll just do the the y direction. I'm just coming along here, and I'm just taking this component, the y component of R1, and I'm going to stop right there. And then I'm going to take the y component of R2, right? And I'm going to stop right there. And then I'm going to flip around, and I'm going to take the y component of R3 and go right back down there, right? So provided I stay constrained just linear motion in the y direction, that's the component of R1 in the y direction, that's the component of R2 in the y direction, and that's the component of R3 in the y direction, and the sum works exactly the same way. So I can do it in the x direction as well, but this is starting to get a little messy, so we'll just do it mathematically. So R1 in the x-hat direction plus x2 in the x-hat direction plus, let's see, R1 in the x-hat plus R2 in the x-hat plus, there we go, R3 in the x-hat direction. That gives me a sum of 0. And in the y direction, I can do essentially the same thing. So R1 in the y hat plus R2 in the y hat plus R3 in the y hat equals 0. So with the second expression, really all I've done is just walk there to get to R1 in the y hat, there to get to R2 in the y hat, and then all the way back down to the origin, which is R3 in the y hat direction. Okay, so once you get this far and appreciate that these are the expressions for the vectors, the next thing to do is to ask the question, well, what happens if there's some uncertainty in the direction that the vector points? So how to handle some small uncertainty about where the vectors point. Okay, so that's the question we're going to answer. And the way that we're going to try to answer that question is we're going to draw each individual vector, and then we're going to draw a little deviation in that vector. So let me draw the same surface here. So here's the same flat surface. Okay, my same coordinate system, y hat, x hat, and the same origin. And I'm going to try to represent the vectors in a very similar way that I did up here so that this is more or less self-consistent. And so I'm going to draw R1 like so. So there's R1. Now, we're going to try to give R1 a small amount of uncertainty. So what that actually means is that the true R1 might point off maybe in this direction, might point off maybe in this direction. I don't really know. But the way that I'm going to represent that is with another R1 vector. So I'm going to have this very intentionally kind of go off in this direction. And I'm going to draw this one quite a bit shorter, right? Because R1 is essentially our main vector, and then there's a little bit of uncertainty in where it lands exactly. And so this smaller R1, which we will refer to as delta R1, represents the tolerance of where that vector lands. Okay, so now if that vector actually lands there, then what does my R2 look like? Well, R2, remember, kind of goes off in this direction. So there's R2. And I'm going to kind of ask the same question. What happens if there's some uncertainty in R2, right? R2 maybe points here, maybe it points there. I'm not really sure. So I'm going to represent that uncertainty in the final location of the end of R2 as another very small vector. And we're going to call this delta R2. And then we're going to draw the same R3 that we drew before. Remember, so R3 is this return vector whose purpose is to go back to the origin. So remember, R3 kind of has a steep slope and goes back in the direction of the origin. But now remember, if I draw that same vector right here, there's uncertainty in R1 and uncertainty in R2. So if I try to draw that same vector, I don't quite get back to the origin. Right? I'm going to try to draw it as close as possible to the original. There it is. Okay, like that. And we're going to call that R3. But now, oops, I haven't actually made it back to the origin because this R3 vector is meant to be the same as this R3 vector up here. And so to get back to the origin, I also have to give myself a little bit of leeway and create an additional vector to get me back to the origin, which we're going to call delta R3. Okay, so I've got my now 6 vectors 3 principal vectors and 3 vectors that account for the uncertainty in the principal vectors. So I'm just going to remind myself here in words that R sub I, this represents a nominal dimension, or just a nominal vector, and then delta R sub I represents the deviation in R sub I. And it turns out that these deviations are also tolerances. When you break them down into the x coordinate system and the y coordinate system like we've done up here. Okay, so now if I were to write out the same x direction and y direction expression for this figure as I did for here, it's going to be slightly more complicated. It's going to look like this. And in fact, I'm going to get a fresh sheet of paper so that I can draw it completely here. So let's just bring this guy over so that we can keep looking at him. Okay, so I'm going to draw the stack up of tolerances here, or stack up of vectors here. So this is going to be the sum in the x hat direction for R, and it's going to be R1 in the x hat direction plus now delta R1 in the x hat direction plus R2 in the x hat direction plus delta R2 in the x hat direction, and then the final term is going to be R3 in the x hat direction, and then plus delta R3 in the x hat direction. And just like before, those guys, when I sum them up, get me back to the origin, and so the sum of these guys is equal to 0. And the same thing is true in the y direction. So I'm going to have R hat, R1 y hat plus delta R1 y hat plus R2 y hat plus delta R2 y hat plus R3 y hat plus delta R3 y hat. And again, if I walk around this loop and I'm just doing it in the y direction, the y hat direction, I go up a little more, up some more, and then down, 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 and back to the origin. So this is going to get me to 0. Okay, so that's really all I want to show. The underpinning math is that if you take a closed loop, a closure, set of closure equations, by just summing up the vectors from an origin out to some point and then giving yourself a return vector to get you back to the origin, when you add them up, you get 0. You can break them down into the x component and the y component, and you still get 0. And then you can even account for uncertainty in those dimensions, uncertainty in where those vectors actually land. But if you create a situation where you're always wanting to get back to the origin, they still sum to 0. So that's really kind of the fundamental basis underpinning how these tolerance loops work. So the final result for our purposes is that we can represent a tolerance stack up as a summation of vectors and the deviations in those vectors in one ordinate direction. Okay, so ultimately, we're going to use these two equations, this guy in the x direction and this one in the y direction, to develop our tolerance loop equations. So that was the math that I wanted to show you. As you can see now, not too bad. And we'll pick this back up again with an example problem where I show you how to apply this to figure out what those tolerances on the dimensions actually need to be. That's it. Thanks for your attention.